Okay, continuing on with question 4, we've got a question here that's actually come from one of the old spec mechanics papers. So it's got a little bit of a mechanics feel, but we have everything we need in our pure maths in order to answer it. So we get given a model boat that's moving with this velocity, and we get given a position where it is initially. So we're asked here about the speed of A. So the speed is to do with its velocity, it's the length of its velocity. Nothing to do with its position, so we just need to work out the length of this vector. So question 4. We're given a vector here, we just need to find its length. So this is minus I plus 6j. Probably very bored of hearing me say it, but make sure you underline your vectors. And this is the vector v. So our speed is just the length of this, so it's the square root of minus 1 squared plus 6 squared. Which gives us square root 37. Remembering that this minus 1 squared, if you do it on a calculator, your calculator will do the squaring before the minusing, so you have to put it in brackets. So if you ended up with 35, that's a minus problem. The direction in which A is moving, giving your answer as a bearing. This is really important to start drawing this. So I'm just going to draw, let's just assume it's here. Its velocity, that tells us how it moves. It's moving minus 1, so that's 1 to the west. And then it's moving 6j, so this is north 6, so it's moving up to here. So this is 6, this is minus 1. So we're asked to find it as a bearing here. We actually need to find this angle all the way around to here, because that's how bearings are measured. They're measured clockwise every single time from north. So what we've got is essentially a triangle here. So this has got an opposite of 6 and an adjacent of 1, and this will give us this angle in here. So because we've got the opposite and the adjacent, we're going to use tan. So for part B, tan theta equals opposite 6, adjacent 1. This gives us that theta equals, we're going to use tan minus 1, so on our calculator, tan minus 1, 6. We don't need to put the over 1 bit in. This gives us an answer of 80.537. Once we've got this, we just need to work out the actual bearing. So we have to add on 270 to this. So 270 plus theta equals, if I add 270, I get 350.537. One of the conventions with bearings is we also give it to the nearest whole degree. So this is 351 as our bearing. C. For parts T, we're given at time t equals 0 a second boat is at point B with position vector this. We're now going to have to take into account position, not just speed, and this has got a velocity as well, to show that A and B will collide at point B and point P. So we need to draw ourselves a little diagram to start off with. So in our general position, this one starts off at 2 minus 10, so 2 along here, minus 10 down here, and this is A. And this is moving this way. We worked out over here, it's moving roughly that way. So we've got another one here that starts at minus 26.4, so this is minus 26.4, so over here somewhere. And this has got a 3i plus 4j, so it goes along 3, for every 4 it goes up. So this is going to be heading that way, so this is B, and here is our point P. So in order to do this, we need to use basic speed, distance, time. We don't need to use any fancy mechanics stuff, we just need to use speed, distance, time. So this one starts off with a position there, and every second it moves this much. So its position is going to be given by this times however many seconds it's moved for. So for A, we get 2i minus 10j, because that's its position, plus every second, so we don't know how many seconds it is, we're going to call it t, it moves minus I plus 6j. We're now going to do exactly the same for b. This starts off with a position vector here, minus 26i plus 4j, and every t seconds it moves 3i plus 4j. So that gives us two different things. We know at position P they're at the same place, which means these two positions must be the same. This gives us one giant equation that I'm going to start writing down here. So 2i minus 10j plus ti plus 6j equals minus 26i plus 4j plus t 3i plus 4j. Okay, I actually missed a minus sign here, so we're going to have a go at this bit again. So we've got this equation that we've made by making our two things equal to each other. A was just somewhere down here before we had to change this line. So we know that this is true for all i's and j's and t's, which gives me an equation for i's. So we've got 2i, 2 minus t here equals minus 26, and here we've got 3t. This now gives me an equation that I can put together and work out a value of t. So if I add the t over, add that over, I get 4t equals 28, I get t equals 7. Because this needs to be true for the j's as well, I also have to check it works for j. So for j's we've got minus 10 plus 6t equals, and on this side we've got 4 plus, and we've got 4t. This also needs to give me t equals 7, or they won't be in the same j position. So if we subtract this 4t, I get 2t equals, if I add the 10 over, I get 14. And this indeed gives me t equals 7. Because we know they have the same j component, the same I component at the same time, this means they collide. For the last bit, all we need to do is work out a position vector for p. We've got our two equations of motion here that tell us where it is at any given time t, so I'm just going to put 7 into any one of these equations. So I get 2i minus 10j equals plus 7 minus I plus 6j. To collect this all up together, we have 2 minus 7 is minus 5i plus, we know that minus 10 plus 42 is plus 32j. And we're finished.